Today we'll continue our discussion of the relation between some smooth dynamical systems and the symbolic ones like Markov chains. And last time we have discussed the following example. We have, let me recall this. We have this map. So it is just a linear map on a torus, on a two-dimensional torus. And we have the torus as a vector space of a plane under a lattice, which is Z2. And we consider the linear map on a plane, which, if the matrix is from GL to Z, induces a map on a torus. And bijection and diffeomorphism, whatever, on a two-dimensional torus. So we consider this initial linear map to be defined by the matrix 2, 1, 1, 1. In fact, one can consider any matrix with the following properties. The properties would be that this A has two eigenvalues, and we require that these eigenvalues, since the determinant of A is plus or minus 1, this means that the product of the absolute values is equal to 1. Therefore, there are two possibilities. One possibility is that they lie on the opposite side of 1, and another example, another case is that both of them have the eigenvalue equal to 1, have absolute value equal to 1. The last case can be further decomposed in the case when we have some eigenvalues equal to 1, and another case when two eigenvalues are complex conjugated. And then obviously the absolute values are equal, and hence they both should be absolute values should be equal to 1. But we don't need this case. We will consider this case. This is usually called hyperbolic case. In fact, if you consider the action of this map on a plane, this linear map on a plane, we have quite a simple dynamics. Let us assume for simplicity that both lambda1 and lambda2 are positive. Otherwise, we can just pass to the second iteration and everything will be the same. So if we assume that both eigenvalues are positive, then we have two one-dimensional eigenspaces, and along one eigenspace you have a contraction, and along another eigenspace you have an expansion, and this is the dynamics. So if you look, for example, at the trajectory of one point, then you have a sequence that goes from one this eigenspace to another eigenspace. It more or less, it lies. In fact, this this trajectory lies on some curve which is more or less hyperbola. In fact, it is a trivial generalization of hyperbola, y equal to the x to some power mu, with mu is where mu is negative number. In these coordinates, so we have, for example, an expansion here, contraction here, and so the orbit works like this. So So this is the dynamics of this map in the plane. And now we can pass to the torus. In a torus, we have quite an interesting situation, because we consider, say, a unit square here, and then, in fact, the dynamics outside should be compressed into this square. So, for example, this line can be now drawn inside this square. So when you go here, you continue from here, and so on. So in particular, one can easily prove that this line has an irrational angle, so it cannot form a circle. It will fill the square in a dense way, and the same for another line. Then we have proven that, well, not proven but stated, that this dynamics is more or less the same. I will explain this a bit later, what it means by this sort of isomorphism, that this dynamics is the same as the dynamics of a Markov chain, with some appropriately chosen Markov measure on the space of sequences. So we have here at the bottom, we have a Markov chain. This means that you have some P. Well, let's some matrix of transitional probabilities and some stationary distribution. And this obviously define a measure on a space of bi-infinite sequences of states. So to define this measure, you just say that if you fix some, so if you consider the set of all such sequences, infinite in both directions, the set of such sequences that at some fixed segment of indices have prescribed values, so xi equals a naught, x I plus k equals to ak. If you have this, then you should just say that this is a probability, the usual Markov probability. So it is a probability that you start at the moment at the state a naught, and then you have just the product of transitional probabilities. Then, well, and sigma is just a shift to the left. So just the change of index by 1. So, and I say that that if we have the system on a torus that was described above, then we have what is drawn here. So the dynamics is conjugated to the dynamics of some Markov chain, and the conjugacy map is in fact maps this. So it takes the Lebesgue so under this map, the Lebesgue measure in the image corresponds to this Markov measure at the preimage. So this was the statement, and we started to construct this. And first, our observation was the following. This is, in fact, the general thing when you consider some, if you want to construct some coding of such sort, to any symbolic system, you can just explain how to. So it is a bit more a bit easier to think about the opposite map. It is not well defined, in fact, because some sequences just glue together under H. So we have no proper H to -1, but let us now don't be too strict here. Then I just need to explain how to define X. So I have some point, say X. So let me say this. So I have some point X here, and I want to explain how to construct the whole sequence omega n, which corresponds to X. But in fact, I just need to construct omega naught, because if I have this map, then I can, for example, take Tx, and Tx should correspond to the shifted sequence. So it's so if this is, for example, some f, then the same f for the point Tx will take omega 1, and so on. So in fact, the whole information about this this map is concentrated in just one piece of information, in the information how to construct omega naught. And so if this information just means that I split the torus into some parts, just cut it into some pieces, and on each piece our omega naught is one of our states. So there is the set of, so I can say that A J is a set of all X such that f of X equal to J. This is just the same as to, so I just need to construct these AJs. And then if I somehow fix these AJs, I can write down this formula, which is exactly what I have already said, that if I know that my map should, so if I know that this diagram should be commutative, this diagram, then this is the only way I can do this. So this was a preliminary. This was just a general recipe. What are the problems here? The problems here are the following. First of all, this set can be empty, and this. Note that in this formula, it is much easier to think that we have a sequence omega n, and then we construct X corresponding to this sequence. So it goes in good direction in this. So we can have some sequence omega n, then we consider this intersection, and it is empty. This is a problem. Another case, which is also not so good, is when this intersection contains of 2 or more points. This is so we have to prove that if we choose AJs wisely, then these problems will disappear. In fact, we need a bit more delicate definition. Our AJs will slightly intersect. In fact, they're just rectangles, closed rectangles on a torus, or to be in general case parallelograms. And so they will have some pieces of boundary which are shared by 2 adjacent parallelograms. Therefore, this this definition is not too good for this, and the correct definition is written here. So we will use this. So again, we start with some AJs. Then for any sequence omega k, we can then define this set, this right-hand side. Then we have some set, and we hope that for any omega k that is allowed by our Markov chain, this set contains only one point, and then this point is h. So h, so x is h of omega. This is an idea of this construction. Okay. So I have to construct this a omega k such that this intersection contains only one point. And this was, so we have started last time to do this. And we started with, our first attempt was to construct the decomposition of a torus into two rectangles. In fact, in this case, you can even think that they are squares. So this is this decomposition, and here I have drawn how the images of these rectangles will lie inside this R2. So if we so here is well, let me explain again. Here it is. So here is R1, and here is R2. Now let us look only on R2, and now we can consider say the image of TR1. So the image of R1, which is this orange rectangle here. Here it is, and we have seen that it starts here, and then it crosses this bottom part of R2. So let me draw it like this. The same for the for this purple rectangle, which is the image of R2, and this image starts here. Then it goes here, and then it ends here. And so our first attempt was to consider this R2 and this R1 and R2 as to our sets as A1 and A2. But we have seen that the intersection is not good. It contains too many points. Now, what can I say? What have I said next? The next thing is that if we consider these 5 rectangles, these 5 intersections. So proposition, this decomposition into 5 rectangles is Markov defines Markov coding. So let me start again with a consideration of combinatorics, of how these five rectangles intersects with their images. So let us consider any one rectangle. So if you want to say A4, and let us consider say TA4. Where this TA4 lies? Well, we can see that this TA4 lies inside TR2. Well, so A4 lies inside R2. It looks like this. And therefore, for images, we have the same picture. For the images, we have TA4 lies inside TR2. So we have okay, but then we can draw it on the same figure here. So we see that this teal stripe, this teal stripe will intersect the whole purple rectangle. So we have the TA4 will lie here. Then it goes here. Then it goes here. Therefore, we have the following claim. And of course, the same can be drawn for any other image of AJs. So we have proven, in fact, the following claim. Let us draw it right down here. Okay. If we intersect interiors of our domain, so in the interior of AI with AJ is either empty set. For example, we see that, I'm sorry, here's T. For example, we have seen that this intersection is 0 when I take the interior of A5 in intersection with this TA4. Or a rectangle such that well, now I can say that this I want to describe how this rectangle lies in each of two of these rectangles. Well, that lies in AI as follows. So this is AI, and let me also draw another figure for T AJ, and the intersection is something like this. There's some stripe here and some stripe here. What is important that this stripe goes from one side to another side of this rectangle. Well, let me say that this direction is the direction of the unstable direction. This is a stable direction. Inside AI, this intersection is a stripe that goes all the way along the EU. So it starts with some segment on the boundary that is parallel to ES and then goes throughout this rectangle. And the same, but vice versa for the image. It is a fixed segment on the side that is parallel to EU, and then it goes all the way along ES. So why is this so important? Well, let us consider a triple intersection. So, by the way, I can now say that this let me say that okay. I want to consider this this formula. Yes, so I want to consider the intersection. Well, let me say start with say the following: some AI naught intersection with t minus 1 of AI1. Sorry. Yes. Okay, and the intersection with t2 minus 2 of A2. So we have three states, I1 and I0, I1 and I2, and want to consider this intersection. Of course, I just use the intersect only the interiors. So HA. This is just the interior, just to write it down in a shorter way. Okay. In fact, we have already proved some of this thing. So let me start with this rectangle. Then, if we consider this part, then, well, this is essentially the same as the claim we have just stated, but when applied t2 minus 1 to both elements. Therefore, this looks like this. So this intersection, the intersection of these two rectangles, looks like this. This is a stripe of this direction. On the other hand, if we consider this intersection, we can say that this is just a transformed intersection of the form AI2, sorry, AI1, well, AI2 intersected with TAI1. Therefore, here we have this figure, the right one. And therefore, inside this, it is a vertical stripe. Well, why is it so important? It is important due to the following. First of all, we can say that, well, let's start with the following. Let us define some metrics. Well, let's see. Mij, which is 0 if this intersection is non-zero, is non-empty, and if it is empty, it is 0. Case 1. If these intersections if this intersection is empty, well, then the whole intersection is also empty. And if this, so if Mi naught, if this equals 0, then the whole intersection is empty. So let us assume that this equals 1. And let us also assume that this equals 1. Because otherwise, again, the intersection is 0, is empty. And in this case, we have the following. That this intersection is this. What can I say now? I can consider the following claim. So this is the whole intersection. So the next claim. Let me consider now some intersection of K. Well, let me say this. Well, let us consider now the intersection of several consecutive terms. Then I again say that this intersection is a rectangle. And what can also be said about it is that it is a stripe again that looks almost which lies in its first term and its last term, t minus ka omega k, and t minus la omega l, as follows. So we have this first term, and this is like this. And we also have t minus la omega l. And our intersection is a stripe here and a stripe here. And in fact, so we have just proven this claim for the simplest case when we have just 3 terms. So for 2 terms, it was done here. Then here, in fact, we have proven this for 3 terms because we just take these 2 intersections, these pairwise intersections, and then from this figure that inside t2 minus 1 of I1, we have seen that this claim is true. Well, in fact, the first term, so now if I want to draw this, then this is in fact a long, looks like this. So inside this long teal stripe, we first consider its part that lies inside the blue rectangle. This is a somewhat smaller stripe, and inside this stripe, we take another stripe, the intersection of the blue rectangle with the orange one, and this intersection cuts substripe inside this inside this. So for n equal to 3, this claim, so for three rectangles, this is true. And then you can continue this argument, adding one more rectangle for each time. So we start with in fact, this is let me just skip it. It is not so difficult to prove. You just add one more. So we have this. Okay, let us now consider the T2 minus L plus 1. Yes, so we want to consider now the next term. So we want to add here T2 minus L plus 1 A omega L plus 1. Where it is? Well, we know that the intersection of the last two terms in this vertical stripe. And therefore, this the whole intersection is this. Well, okay, then it is easy to see that this the whole intersection is a horizontal stripe in this last term. So the whole intersection is a horizontal stripe in this. And on the other hand, it is a vertical stripe here. And therefore, the claim is true. Okay. And this means that when we consider, so now let us go back to this formula. This formula, we see that if omega k is an allowed sequence, so we assume that m omega k plus 1 equals 1 for any k. This is our, in fact, the set of all such omegas is just sigma m. Is the space of our Markov chain. And we see that then these intersections are just rectangles, smaller and smaller rectangles, in fact. And so, but these intersections are always non-empty. And here we have a sequence of compact sets, decreasing sequence of compact sets. And you know that such a sequence of sets have a common point. So this intersection is non-empty. And that's it. Therefore, and since the diameter of this set goes to 0, we have that this intersection can contain only one point. Therefore, we have proven that this definition is well defined, is correct, works for any sequence from sigma m. Okay, so it works, and a bit more about, well, let me conclude the proof of our theorem. In fact, it is also clear that this H is a continuous map. Well, sigma m is a compact subset of the sigma of sigma 5 of the set of all sequences of 1, 2, 3, 4, 5 by of these by infinite sequences with a so-called Tikhonov topology. We have discussed it before, and therefore this set is well, this is a topological space, and we see that this H is then continuous, just because the pre-image of so if we want to, we see that if we fix a long sequence, a long segment of our sequence, say we know omega from the position omega minus n to position omega n, then all the images, all h of omega for such omega lies in a very, very small rectangle. And therefore, this map is continuous. Finally, I have stated here that the Lebesgue measure maps to mu. Well, this is again is not too difficult. The idea is the following. So let me again. It may be a bit easier to see this from these figures. So look, we have. Let us now consider this the Lebesgue measure on a torus. What we have then? We see that the following is true, that the measure of all this intersection, well, let's consider the intersection from I equals to minus k, from I equals to k to I equals to L. Well, the measure of this intersection, well, Lebesgue measure, divided by Lebesgue measure of the a bit shorter intersection. Then this this ratio is a ratio of this the back of this orange thing divided by the well, vice versa. The back of this divided by the back of this. Okay, from here. Oh, I'm sorry. No. This is a ratio of this this divided by the Lebesgue of this. But you see that this equals to the ratio of Lebesgue of this divided by Lebesgue of the whole orange rectangle. Therefore, but by the way, so well, this is because this is just the area of rectangle. The area of rectangle is a product of its bases, and so when we go from the numerator to denominator, we have just we have the same vertical side, and the horizontal side is changed from this to this. And therefore, these ratios are the same. But this ratio is fixed. It doesn't depend on anything. It's just, in fact, one can say that this is pi omega L plus 1, well, by definition. And we have, so if we define this transition probabilities as follows, then we have seen that the Lebesgue measures here is the same, but on the other hand, we can rewrite this ratio. So when we go to the go upwards to our to our symbolic space, to the space of sequences, we have the measure of all such x, such that x, well, such that okay, now the set of all sequences such that alpha k equals omega k and so on to alpha L plus 1 equals to omega L plus 1 divided by the same for the set of sequences when we fix only these positions. And then we have that this ratio is just pi omega L plus 1, which means that you can say that the when you add one additional condition on the right, then you just multiply the probability by this element of the matrix, and therefore this is a Markov measure. And then you need a bit more consideration to show that your matrix P, your matrix pi is stochastic, that you have a stationary distribution, which is just the areas, the Lebesgue measures of our initial rectangles, AJs. So by the way, P stationary distribution is just the Lebesgue of. And then you can prove that everything works here as needed. So this is the proof of this theorem. We have seen that the dynamics of this nice smooth map on a torus is just the same, more or less, as the dynamics of the map on just the dynamic of a Markov chain. This can be then one can, for example, say that some stochastic, some ergodic properties of the initial map are more or less the same, or in fact the same, because this when we consider any particular example, as for the Markov chain. And for the Markov chain, the situation is quite close to just independent variables. So, for example, we have for Markov chain, we have a central limit theorem, and so we have the same central limit theorem for the for our map of a torus. This is one possible way of argument how to construct this how to deal with the central limit theorems for the smooth dynamical systems, for some of them. And this was some exact proofs. Next time we will discuss the central limit theorem for Markov chains. And today I want to have some sort of, I don't know, short glance to what is hyperbolic dynamics. We have seen that this, at least now it can be guessed that this detailed consideration. So we have a very fixed, very precise map of a torus. Well, the linear map with hyperbolic matrix. That's it. And then for this, for only one or for very small number of maps, you can consider you can construct this conjugacy to the Markov chain. But in fact, and this was a discovery of 1960s, was that this is not so unique. For example, if you perturb this nice linear map, then exactly the same thing will hold. Well, maybe with some corrections, but nevertheless. Let me now explain what was done in 1960s in this domain. Here, this is the part of my talks that will, so that where I will almost omit any proofs, maybe only some definitions and maybe some sketches. This is called hyperbolic systems. And this is the following. So let M be a smooth manifold. And I assume that at this smooth manifold we have some Riemannian matrix. So at each tangent space we have a scalar product, a Euclidean scalar product, and it depends continuously or smoothly. Let me say that this manifold is compact and closed. This means that it has no edge, no band, and and it is compact. So at each point we have this Riemannian matrix. So on each space. In fact, the definition below will not, in fact, depend on the choice of this Riemannian metric. If you replace it with something that is with some another smooth Riemannian metric, the result is the same. Okay, so we have some map. Well, T is, well, let me say is a Nosov map. Just is a Nosov, and if the following holds. So first of all, for any point, we have a decomposition of a tangent space for any P. There exists a decomposition of our tangent space into the direct product of two spaces, of EU and EES. For our in our case, in our linear case, this decomposition was just the same for any point. We have ES is what goes along the stable is a stable eigenspace, the eigenspace that corresponds to the eigenvalue with absolute value less than 1. And EU is an unstable eigenspace that corresponds to the unstable eigenvalue, that is the one which is larger than 1 by absolute value. So, well, and let's assume that this decomposition is continuous. In fact, again, this can be relaxed somehow, but nevertheless. Okay, the next thing is that this decomposition is invariant. This means that T well, we say that this is a diffeomorphism. And the same for it. And the third thing is that when we consider any vector in ES, then we can consider its image under the iteration. And then if we consider a norm, well, there exists some constant C lambda which is larger than 1, such that this is not more than C lambda to the minus n normal for any n non-negative. And for any v in ES, the same holds for negative powers. So, informally speaking, any vector in ES, if we iterate it with our map, it contracts exponentially fast. And for any vector in EU, contracts exponentially fast when we iterate it back with t to minus 1. That's it. In fact, this can be generalized further when all what is written here is not for all points at our space, but for some subset. This is also an interesting case when we have this only for some compact set inside our space. But let us consider only this case. So this definition again does not look very stable. So when we perturb our map, of course, everything is destroyed. You have no longer an invariant, so the same decomposition into these stable and unstable spaces is no longer invariant. So, for example, this will be failed. Will fail here. But in fact, one can somehow somehow prove that this definition can be restated in a way that is robust under this perturbation. Well, let me. Okay. So the definition, so the corresponding result is called so-called comn condition. There exists a field of cones. Let me say that an unstable cone is a set Q at some point P is a set of all vectors such that its unstable part is much longer than the stable one. So VU absolute value is larger than C. So this is a cone. And the same for the stable cone. So by the way, if you take, for example, if the dimensions of these spaces are 1 and 2, as for, so if unstable space has a dimension 1 and stable space have a dimension 2, then a stable cone, then unstable cone is this. The cone is the part that is what is usually a thing by the cone, but by the cone with its interior. And an unstable cone is this weird part, which is not normally considered a cone, but here it is. Okay, so the idea is that the cone is some set that contains EU or ES and it is somehow a neighborhood of this. Okay. Then we can say that T is Anosov if and only if there exists a family of cones such that first of all, again, T star of KSP lies strictly inside S of TP for U. And for S is the same, but for the -1. And moreover, for any V in KP, the norm of the image okay. The second condition is a bit delicate. There exists a good Riemannian metric such that this is like this. There exists lambda positive, more than one. So every vector is stretched by some some number of times that was bounded away from one. And the same for S and T to minus 1. This is the definition. And here it is quite obvious that if you perturb your map, then these conditions will still hold. Well, for example, you have a cone here at point P, and its image under T star. So we have this cone. This is KP, and this is KUTP. And its image is some cone that goes like this, lies inside it. And you have some stretching. Then when you perturb your map a bit, this image, well, let's say T epsilon, so some perturbation. Well, it is somewhat close to this. But nevertheless, it's still, if the perturbation is small, it is still inside this, our cone field, inside the corresponding cone. And the same if there was some stretching, then it's still some stretching, but maybe with a bit smaller constant. Well, because, you know, the difference is quite small. So this is an idea, and I don't want to dwell too deep into details. So what I want to say is the following theorem. That let A be a Nosov, well, let T be a Nosov, and topologically transitive. The latter means that if you have 1 point, so if you want to go from the neighborhood of 1 point to the neighborhood of another, then it is always possible. So for any U and V open non-empty, there exists some N such that this, so you can go from U to V, from V to U by some iterations of T. Then T has Markov coding. So exactly as above, in this topological sense. So we have this, our manifold M, we have this map, we have some have everything like this, but only in topological sense, that the map, that this H is continuous. It is continuous at it, and it so for almost all points the preimage is just one point, but there are some cases when we have the preimages with more than one point. This is not so you see in our example that this is quite natural, because of course this H cannot be a diffeomorphism, because M is a nice manifold and sigma A is totally disconnected space. It's something like Cantor space. Okay, but this is not too good for our ergodic discussion, because of the following. You have we want to have an invariant measure. Well, initially there are no such measure. So in our example, we started with Lebesgue measure for T, and then we go, we see that the image of this Lebesgue measure, the pre-image of this Lebesgue measure under H is just the Markov measure. But now we have no invariant measure initially, and we need to somehow construct this. Note, so we can construct many such measures. Just take any for our topological Markov chain and push forward it by H. But of course, these measures are not to. It seems that there are some of them are more natural than the others, and in particular, there is one interesting measure which is called Perry measure. So let me, before the discussion of Perry measure, said that the measures. So what we do need? We need an invariant measure on a topological Markov chain. So sigma A is just the set of all sequences without forbidden two-letter words, so that every transition from omega k to omega k plus 1 is allowed from the set of our allowed transitions. And I want to so there are many. So now, if I take any Markov measure, if I prescribe any transition probabilities compatible with this allowed and not allowed transitions, we have an invariant measure and a Markov measure. So there are continuum of these measures, of these invariant measures. But moreover, this is just a small set of the small part of the whole space of invariant measures for this set, because for example, you can consider much more complicated measures. You can take what is, for example, what is called a Markov chain of some order. You can say that the probability of transition depends not on one space, on one state, but on two previous spaces. So we have so your transition probability depends on the where you are now and where you were the previous day. And then so we have, again, it is quite easy to construct this the requirements for this transition probabilities, and you have this this setting. In fact, this can be reduced back to the normal Markov measures as follows. You just say that if you have a sequence omega n, you can consider a new sequence. Well, let me write it as follows. Omega n is omega n plus 1. And then you have a sequence omega n. And here you can, on this set, you can define your Markov measure, which will be described exactly as I have said on the space of omega small. You just say that, so for omega n, for omega large, you have that the probability to go to some space, to some state depends on your current state, but your current state is omega n plus 1. And the probability of going from this to this is some number. Well, first of all, it is 0 if omega n plus 1 prime is not equal to omega n plus 1, and it's some number p omega n plus 1, omega n plus 2 otherwise. So which is just p omega n plus 1. So this is a way how we can construct the measures, the Markov measures of any finite order order 2, order 3, and so on our set of sequences. And even this is not the whole space of measures, because we can. There are many others. In fact, there is no reasonable way to expect any descriptions of the whole invariant measures or even the whole ergodic measures, the whole set of ergodic measures for such a rich dynamically, for a system which is so rich dynamically. So nevertheless, among all these measures, there is one measure which is somehow unique. It is somewhat optimal. And I'll start not with this definition, but with some definition that is that it has nothing with this optimality. The definition is the following. We have that the probability of omega. This is a shift invariant Borel measure such that the probability of some sequence. So you say that at some moment you are at omega n, then you're at omega n plus 1, and so on. Then you are at omega n plus L. And this probability is some function that depends only on three things. First of all, on the length of the sequence. Secondly, on the initial state, and thirdly, on the final state. Well, of course, it is 0 if omega n plus 1 is not admissible. This means that for some pair of adjacent indices, you have aij a omega k plus 1 equals 0. If so, then this probability is definitely 0. So here is a definition. The probability of any concrete path from one state to another depends only on the initial vertex on this path, the final vertex, and the length. That's it. What is how to do this? In fact, to have this measure, we need the following assumption. That is that let me require a bit more than needed. I will require that for large there exists some n such that a to the n is positive. This means that there exists such n such that from for any two vertices there exists a path from I to j of length n. Well, because for example, it is possible that you have some two sets of vertices and one set of states lives its own way, its own life, and another is completely separate, and this is not good. Under this assumption, this pair measure exists, and the construction is not too difficult. In fact, it is the following. Well, we have this matrix A. A is a matrix of non-negative. It is the matrix of zeros and ones, but at least all its entries are non-negative. For such matrices, there is so-called Verbanium theorem that says that there is an eigenvalue and eigenvectors that have non-negative coordinates. And in fact, this lambda, which is called the Frobenius eigenvalue, is the largest in terms of absolute value among all eigenvalues of A. Also, we can apply the same for the transposed matrix. So Q and E belongs to R plus to the dimension, D, where D is a number of our states. Okay, and moreover, our assumption R plus is, let me say this as follows. And in fact, this condition that there is a power that is positive means that all elements of all Qj Vj are strictly positive. This is because if you write down that Qj equals to, say, a to the n of Q, J, you see that Qj is a linear combination of all elements of Q with non-negative, with positive, strictly positive weights. And since, of course, Q is not identically zero, we have this. We have the total sum is positive. And then one can consider the following transition probability. And the following well, let us assume that QV equals 1. This is just a normalization condition, because you can always scale Q and V as you want, and you can say that their product equals 1. Then this is the definition of pairing measure. Well, in fact, this is, one can see that this is only measure with this property. Then, of course, you need to check that this Pij, for example, is a stochastic measure. Well, maybe I should. It should be the opposite one. Well, it depends on the definition of everything. Okay, maybe I will, here I am slightly slightly incorrect, but the idea is, so maybe one of the problems will be to write down the correct formulas here, which are quite close to this. Okay, so then this is a stochastic measure. You can prove that it is invariant, and then if you, why do you have this condition? This condition is in fact quite clear from the formula. Look, if you have this, then your probability is p omega n, and then pi omega n plus 1, and so on. And then you have, well, q omega n, v omega n, and then, well, aij, of course, all of these a's are positive, are just ones. Yeah, so we have v omega n plus 1 divided by lambda v omega n. Have just this, and then you see that everything cancels out, and finally you have just q omega n v, well, and this also cancels out, v omega n plus l divided by lambda to the l. That's it. So now I want to explain in what sense this measure is optimal. This is, again, deserves maybe 2 or 3 lectures for the complete exposition, but I'll say the following. Theorem. Pairing measure is a measure of maximal entropy. Well, what does it mean? It means the following: that let us start with, so what is an entropy in this setting? This is quite widely used in the information theory, and the definition is the following. So let us consider some decomposition of our space into some parts. So, well, we have, say, A. then and X mu is a probability space. The definition is that the entropy of this A is just the sum of minus P of AJ times the logarithm of the same. This is a definition. One can so the definition is, at least now, seems something strange. You just take something that is so the formula that just goes from nowhere. But in fact, the reason behind this formula is the following. Let us assume that you need to transmit. So you can, for example, do this as follows. This is so-called Huffman coding. You want to code any state, any AJ, so you get G to some sequence of zeros and ones. And you want now assume that you need to transmit many such sequences. So you have J1, J2, and so on. And so this, of course, gives you the word. So let's be WJ, and so on. I need. So I assume that I can. And I want to transmit this sequence of zeros and ones by some line, and then I want to reconstruct my J's, my set of this. So J belongs to the set of states of this set of indices in my partition. So I want I want the following: that this this reconstruction should be possible, and in fact, this can be done as follows. There is just so I just consume letters from the digits from this sequence one by one. And at some moment, I will say stop. Look at what is in my buffer, and at this moment, so I will see that this is one of WJs. And so then I write down the J1, consume the next symbols, and so on. Then note that, for example, if I have say so. If I want this coding, I need that no word was a prefix for another symbol, for another WJs. For example, I cannot say that the state A, well, let's say that A is 0, B is, well, WA 0, WB is 1, say WC is, and so on. This is not possible because when I take when I see 0, 0, I cannot understand whether this 0, 0 is AA or just C. And one can see that this coding is can be then done as follows. You should just start with an M. You should construct such a tree. So this is 0, this is 1, and again 0 and 1, and somewhere this stops. Well, that's, for example, like this. So this is a code, and here are my letters A, B, C, D, E. For example, here this means that if I see, for example, 0, 1, 0, 0, 0, 1, 0, so on, I should go like this. So 0, 1, 0, and so I have B. Then I have 0, 0, and so I have A. And then I have 0, 1, which is D, and then I have something next, and I need more than this one to decide what is the next letter, and so on. You can see that the following is true, that the sum of the logarithm, in fact, binary logarithm of this length of Lj is, oh, I'm sorry, no. 2 to the minus Lj is equal to 1. Well, this is where Lj is the length of the word Wj. And now assume that you have some probabilities that your next letter, your next state is the following, is the letter that is seen here. So for example, you know that the probability of A is much larger than the probability of B. Then of course, it is reasonable to code A with something shorter and B with something longer. So the average density of this code, so how many digits you need, how many binary digits you need to code one word, is the expectation. So it is a Pj times 2 to the minus L times Lj. And you need to do this. Well, of course, there is a so-called Huffman algorithm that constructs this. But here is a bit, so a step which is purely mathematical. If I assume that Lj's need not be integer, then this is just a problem on conditional extremum, conditional minimum. And you can find this conditional minimum. And this conditional minimum up to some constant, which is something like logarithm of E of the natural logarithm of 2 or something like this, is just this. It's just minus Pj logarithm of Pj. That's it. So this is from this discussion, you can see that this definition is at least reasonable. And then you can do the following. You can consider not only, so we have some partition A, and now you consider, so now your piece of information is that you know where you are at the moment 0, the moment 1, and so on up to some moment. So you can say that your new partition is the following. It is this, which means that you take the set of all is this. You just say that you are at this moment, you have, so you can say that each set of this partition is a set of all x, such that this x belongs to AI naught, is Tx belongs to AI1, and so on. And then I can calculate the entropy of these partitions. An easy calculation show that if, for example, each of these partitions is independent in probabilistic sense, this means that the probability of this is of any set of this form is just a product of probabilities. And you should remember that the probability of image and of pre-image of every set is the same as the probability or measure of the set itself, because our measure is invariant. Then this entropy is just the product of the entropy, so, or in our case, power of our. So this is, so it is natural to assume that, so if you have an independence, then this just grows exponentially. This is just equals to the entropy of the original of the original partition to the power n+1. But in general case, this may be not true, and you can I'm sorry. This is if you have this independence, then this H grows linearly. I'm sorry. It is a logarithmic measure. It grows linearly. And in fact, one can prove that it grows linearly for in any case. And then there exists a limit, which is called H of A. And the final piece of this construction is the following. We can start with many different partitions. For each partition, we can, so this tends to, for any partition, we have this. But in fact, there is a supremum of H of A is H of T. This is the construction of so-called Kolmogorov-Sinai entropy of the measure M. Yeah. This is a definition. It is well known, so heavily studied notion in the theory of dynamical systems, and in particular, it is known that in most cases this last supremum is not needed. You can just take A more or less arbitrarily. You need that this A should, when its images and pre-images should generate the whole sigma algebra, and then everything works. This A, then this supremum equals just H of A for this A. But and there are many others, many other results about this. I just want to say the following. Why do this Perry measure is a measure of maximal entropy? Of course, this is not a proof. I'll just try to explain why is this true. Look, you should consider this. The entropy of this partition. And as I have said, this entropy is an entropy of of the set. So let us assume that our partition is just so now my case. The space is just our sigma A, and A our partition is just the set of all omega not equals j over all j in the alphabet, the set of space, in the set of states of our Markov chain. So I then this then you have this. And by the way, I should say that this sequence G naught and so on to Gn is admissible. Otherwise, this set is just empty. Now I want to discuss the following. Assume that you have this you have this formula, this one. You know the number G, the number J. Well, say J equals to 100. But you can somehow modify PJs as you want. When the entropy is maximal, for what choice of PJs, of course, you see that sum of PJs equals to 1. But for what choice of PJs, this number will be maximal? Well, this means that you need so that the information about the state of your system contains the most of information, is most information rich somehow, so to say. Well, let's explain. So the answer is the following. The maximum is where all these things are equal to each other, and all PJs are just 1 over 100 or 1 over n for the corresponding n. Why is it so? Well, again, this is just the problem on conditional maximum, but this is again quite natural, because for the opposite case, when, for example, you have one state which is just which has a probability very close to 1, and the other states that are have an almost negligible probability, then you see that this is the fact that I say you where at what aj I now so that the point x belongs to some element of this partition. This is not too much information, because in most cases you just say u belongs to this large set, and then well, okay, this happens 99% of time, so why not? And of course there are some states that in case that you landed in this very small set, then this is quite important information, because this is a rare event. But the probability of this is very rare, and so the whole product of this PJ logarithm of PJ is negligible, is still negligible. Well, of course, this is not a proof, but at least an illustration. Okay, and so I just want to say now that for my pairing measure, the probability of paths are not the same. So now, what are my PJs? PJs are the probability of paths from the state of given length L, because I fix omega naught, omega 1, and so on to omega n. So I have that the length of my path is fixed, and that's it. The number of this path is some large number. If my measure is a pairing measure, then then this path have more or less the same measure. Of course, this is not it is not possible that all of them have exactly the same measure, because because these measures are not independent of each other. So there are some linear restrictions, in fact. But these measures are of the same order. They are these probabilities, as you have seen, are this. So of course, for different paths, you have different starting and final point, but well, these products of q omega q starting times qi times wj are somewhat bounded away from 0 and infinity. They say belong 1/100 and 100. And the key asymptotics here is this lambda to the power L. And that's it. Then it is quite natural that for this measure where the paths have that is the elements of our partition have more or less the same measure, you have the same you have more or less the same probability. And that for this measure, for this pairing measure, you have the maximal entropy. So why is this important? This means that there exists one choice of this probability that is dynamically specific, that corresponds to the maximal entropy. So this measure is important is somewhat special, and in fact this how to say this property can be explained without without going to this measure theory. So in fact now there is somehow the property of this maximal entropy is stated. So the maximal entropy itself, for example, is obtained via a very long construction. You start with the map, and then you consider all invariant measures, and then for this, among all these measures, you take the measure with maximal entropy, with maximal Kolmogorov-Sinai entropy as discussed here. But at the very end, you have a number, the entropy of this the maximum, this supremum of all entropies. But in fact, this is so-called variation principle. This number can be obtained differently, without any discussion of measures. Well, let me define this this notion, and this is so-called topological entropy. It should again somehow have this goes along the same line, the same lines. We should somehow measure how rich the dynamics is. Before we have this partition, and then for this partition, you just take the set how the elements of your space goes from one. So how many so-called diaries of your points can be possible. So when the diary is number where at what element of partition you are at the moment 0, then for the image, for the second image, and so on until the time n. And therefore you have this number. But another example, but you can do this even without measure. So the construction is the following. Let us consider, so fix epsilon and n. So my map now is, and this is a metric space. I can consider a set of points. So this is in fact an epsilon, let us say this is an epsilon n net. This is the following. So the set A, well, maybe I should say compact. Of X, so A is then finite, in fact, such that for any Y in X, there exists A such that for any J from from 0 to n minus 1, the distance between t to the j of A and t to the j of Y is less than epsilon. So epsilon n net is the set of points such that the first n, the orbit of length n of any point of your space can be epsilon approximated by the point from our net. So let us consider the following. So let us say h epsilon n is the minimal number of A or epsilon n net. So among all these nets, there is an optimal one with the least number of points. Well, let h epsilon n be this number, and then again I just need to do the following: just take the logarithm of h epsilon n divided by n, and then I should take the limit as n goes to infinity, and then I need to take a limit as epsilon goes to 0, to plus 0. And this is the topological entropy of T. Again, this is the same. So epsilon is some sort of the precision, so the minimal distance that I can see with my eye. So I have not a precise vision. So the slight deviations, so that I go not to the point exactly, but to some point nearby, that's okay. And n is your time. And so again, there are exponentially many variants of behavior of your trajectory at the interval from 0 to n. The base of this exponent asymptotically is this limit, and then you should then try to look with better precision at the same situation, and asymptotically you have h topological. And the theorem, which is variational principle, it says that topological entropy is a supremum over all mu of h mu t. So in this situation, in fact, the topological entropy equals, for example, for Markov chain, the topological entropy equals the entropy of the pairing measure because it is maximum. This is an important thing because you can somehow dynamically choose this measure. In fact, when you can find this measure from this topological procedure epsilon nets. For example, you see that if you somewhere you need many points because their behavior at the long distance is very different, then it seems that your measure is the measure of maximal entropy is concentrated here, because it should, you see that the measure of maximal entropy should focus on the parts of your space with the rich dynamics, where your trajectory is very different, and that's it. This is that your so this is why your the measure of maximal entropy is this. Okay, so now I want to conclude with the following just organizing remarks. First of all, the next time, the next week, we have the last lecture. As I have said before, I will discuss central limit theorem for Markov chains, and as a consequence, I get a central limit theorem for some smooth systems, say for Nosov systems or something like this. And also by the next Thursday, we'll have a set of problems that we can that you can solve, and the week after that, there will be several days to discuss. So you have to send these problems to us in a written form electronically, and then we will discuss them orally with you. And this is our exam. So I hope that so if even so that our next Thursday is 16th, and then we have on 23rd we have this formal time for exam. But if there are it can be spread along the day or maybe several days, because we have different schedules. But anyhow, by the 28th or so, and you should conclude your exam. Well, that's all I want to say for today.